I'm from ARM. And ARM might be kind of a funny company to come speak at Java One, but I think it'll be less funny after you hear my talk. So ARM is actually doing a lot with Java. And in particular, ARM is doing a lot in the Internet of Things these days. And we're really excited about it. So we'll tell a lot about ARM, the Internet of Things, open standards for the Internet of Things. And I actually won't talk very much about Java. I'll just explain why we're using Java as a tool. So we're an end user of Java. We're not one of these, we have this Java platform or web application server or something that we want to sell people around Java. We actually use Java to build real IoT systems for enterprises. And we think it's a great solution for that. So we're going to focus more on what we're doing and then why we do some of that on Java. So my name is Zach Shelby. I'm the Director of Technology for IoT at ARM. I'm located here in San Jose. For the past 2 weeks, the whole 2 weeks, I've been in San Jose. So I'm a newcomer to the Bay Area, so kind of a local, but not. And we're quite a new acquisition to ARM. So I was the founder and CTO of a company called Sensinode for the past 7 years. It was based out of Finland and California. And we were acquired by ARM this summer. So we bring a new dimension to the business that ARM has around software, not hardware cores. So actually we're involved with a business that has nothing to do with designing Cortex cores or the ARM cores that you're using in your phone or in low-power servers today. We actually do software products for the Internet of Things. We'll talk more about that, what we're doing and why. So you hear a lot of people talk about what IoT is, and they think IoT is all these applications, or it's this, or it's not. I've been doing this for 15 years, so I can tell you exactly what IoT is. And you know, it's nothing really special, and I think that's what's different about IoT this time around. When IoT was a hype thing around 2000, early 2000s, everyone was like, oh, IoT is all these automation buses. Siemens had their own, and Honeywell had their own, or it's my sensor network, and I have the coolest wireless mesh network that nobody else can do. It was all this special stuff. Everybody had their special sauce for IoT. And then it kind of went down, and people figured out, well, the Internet's actually really cool. And we can use the Internet and the web to build all these things. And what's happened now, when IoT's come back, is actually IoT is becoming nothing more than the web again and the Internet again. And I think that's what's special about IoT now, is that people have realized that we can and should use Internet tools, transport layer security, all the crypto infrastructure that we have out there, and a lot of the web infrastructure to build these things. So it's nothing special anymore. IoT is the web. But we had to do a lot of smart engineering to make that happen. So it's not that straightforward. We just say it's the web. But we've actually done the engineering to make this happen. And when I'm going to talk about standards and open IoT, we're going to talk about all these standards that we've put together to make web-based IoT a reality. And so my big thing about IoT is that, you know, what we're doing is connecting smart objects. This can be any kind of device. At ARM, we tend to specialize in a lot of enterprise applications. Outdoor lighting, building automation, smart metering, telemetry, vehicles, and otherwise. There's a lot of enterprise applications. Of course, there's things that happen in the home automation and all this, but those are coming more in the future as there's more momentum around these open standards. Home needs a lot of ecosystem to make that work. And what's the goal, right? We make all these devices, these things on the Internet. What's the real goal with devices? It's the service. If we can't get a device working with a service, we don't have a business. We don't have a purpose for the consumer that wants to use this or the enterprise. So we need these things talking to these services. That's the goal. So we should never lose track of that. And what we see happening is that the narrow waist of all this stuff, it's really converging around web technologies. A whole range of REST protocols, web linking, web semantics. So a lot of technologies that we use to put these together. And it turns out they're very similar or reusing the technologies we use on the web today for enterprise applications or just consumer web pages. So it's objects, services, we use web technologies to connect them together. Now, something that we're really excited about at ARM and how we describe what we do is that big data is how we're going to make these services enabled. We need the big data technologies to actually make use of all this information we're getting from devices, make something useful decision for an enterprise or for a consumer. So big data is important, but big data without an information input is nothing, right? Today's big data systems, you're getting your inputs from all kinds of enterprise databases. You have consumer purchasing information. We have all kinds of logs that we can import into Hadoop. That's our big data. But in IoT, it's the little data that we need first so that the big data does its job. And that's what we do at ARM. We're the little data people. So we really like that term. It describes what we do really well. And our goal is to get that little data into the places that enterprise developers need to make big data. So that's the overall theme here. It's little data into big data. And, okay, well, M2M's been around for a while. We've been doing M2M. We've been using IP. But M2M was in a little bit of a chicken and egg problem. They were using a lot of IP technologies, yes, but it's been very stovepiped. It's been my devices and my application. And when that happens, even if you're using internet protocols over cellular, for example, there's this tendency to invent your own stuff. Why not? It's my device and my service. Why don't I invent all my own protocols and own tools and own semantics? I can do that. So you get a bunch of engineers in a room and they'll invent stuff. That's what we do. We're good at that. That's one other thing that's different about IoT. Because we're having this technology available and because we're needing to get a lot more value out of this big data. And I'll explain a little bit later why we need to leverage this big data for value. We're really no longer in the stovepipe mode. We're in the web mode. We have devices. We're able to connect those into services. And we're able to combine those devices. Use the same device in two services. Use one device or use two devices in one service. All combinations of these. And I think this will be a big business enabler in the future. This will be great for developers, great for device manufacturers, service providers. So there's really all upside to this. Some people ask, well, but I still see like my Nest thermostat talking to the Nest cloud service, and so there's still stovepipes. And I'd say that's going to be true from the consumer point of view. You're not always going to see this. This might be hidden under the hood of these things that you buy. If you buy a home automation system in the US, for sure it's going to be locked down into some provider's cloud service. But all that technology under the hood might be sharing that information. It might use the same protocols, same software tools, same enterprise cloud components to make that. So under the hood, we're going to be using shared devices, shared services, web technologies. Something else I think that's important is to understand that when we're doing this end-to-end communications or this IP and web communications, it's really important that we do it end-to-end. So in the past, another kind of pitfall we've fallen into with all this stuff is said that, well, because everybody's using SOAP, XML, XML REST, JSON REST in the web world, the enterprise world, we need to do that all the way down to the devices. And then we need to gateway all this stuff. We'll make this application layer gateway. We put it on an embedded Linux box. We use Java for it, OSGI. And we'll tie all these devices in using an application layer gateway. Well, that didn't work. That was a very broken model because as soon as you change anything on that device, your application gateway just broke. Now you have to change it, upgrade it. It's a huge amount of stuff to maintain. And I can tell you that customers don't want that. So we've had to go away from that model. And what it means is that we actually need to do this communication with web and security all the way down to the end device. And that means to the little sensor device that you're actually getting the data from. All the way down there, we need to get there. And technology-wise, we've gotten to the point that there's no barriers anymore for us to do that. processor technology, even very low power is there, security technology is there, and now protocol technology is there. I'll focus on the protocol technology in this talk. The other reason is business. So what we've seen happening in a lot of these IoT telemetry systems is that cellular, so the actual number of cellular devices, the cellular endpoints going in there, it's linear. And it's not even growing that fast. And so to get in the business and actually gain some value from deploying these systems, you actually have to be working down with the local wireless devices. So we're seeing a really big ratio. In outdoor lighting systems, it's anywhere up to 500 to 1. One cellular router, 500 local mesh devices. That's the ratio actually required by the OEMs manufacturing these systems to make the cost point just right that municipalities will buy these things and deploy them. So we're seeing a 500 to 1 ratio of small local wireless mesh devices. These are small microcontroller-based devices, tens of kilobits per second of bandwidth that these things have to talk IP over, and a small number of cellular devices. So end-to-end will really help us to access all of those devices, manage them, update them. It's good for operators who deploy the systems. They can actually charge for these things. So end-to-end is important, so not only to avoid gateways, but to leverage as many devices as possible. Now, not all IoT applications are created equal. So we'll have applications like smart meters or wellness where there's a very clear value there to the end user, to the consumer. You can charge for that. You can charge for the service to a smart meter. You're avoiding, in the old days, you used to send guys around to read the meters. You remember that? I grew up with that. Used to send the guy to my backyard. He read the meter on the side of my house. We've gotten past that. We've gotten to automated metering. You can read. You can do demand response load control. You can actually save monetary savings to a utility. And you can charge for that. So the value of that is high. But the number of those applications is fairly low. Those are the ones that everybody's going after right now because there's an easy market there. But as you get down here to the long tail, you have a huge number of IoT applications that really don't add a lot of value. They're cool things. I'll turn my lights on when I come home. Oh, I have my cool gadget, or I know what the temperature is out in my yard. Yeah, there's stuff that everybody would feel nice about having, but it's probably stuff that nobody's going to charge you for. Well, what you're going to see happening is that aggregating all that stuff and using a lot of big data technologies, you can actually start to add value to that information. So you'll see people getting into a Google of IoT type of space where Google does this very well with advertisements. They aggregate a lot of that tiny pieces of information, tiny advertising streams into something bigger. You'll see the same here. So by aggregating all this information, you might be able to tell things like, where did somebody buy something? What are they doing with it? How are they behaving? When are people coming home in a neighborhood? And some of that might be new services, advertising or otherwise. Some of it might be just better municipal planning, right? How do you plan the traffic flows in a city based on how people come home at the end of the day? Things like that can be derived from this big data. So lots of kind of low-value IoT applications will need a lot of big data aggregation to actually gain value from those. That's another trend that we see happening. Now, we've had a pretty nicely growing market around this internet in general. So we've seen, between mobile phones and internet devices, market's been growing pretty nicely. And what we want out of IoT is we want a lot more of that, right? We want to see lots of these devices get deployed, integrated into services. We can use those. But there's a risk. And that risk is if we don't actually achieve what the vision I gave you in the beginning, which is that we actually combine all these things together with web technologies. We make these reusable, all the technology easy to gain access to. If we actually continue on the M2M path where we're not really doing anything new there, we're just kind of doing status quo. A lot of stovepipes, everybody wants to do their own protocols. What we're going to see happening is kind of mediocre growth. IoT won't really take off. It'll be a bunch of stovepipe applications. It'll stay pretty fragmented. And that won't be good for developers or anybody in the industry. But if we do a few things right, we think, at ARM, I think a lot of people in the industry agree with us, we think that we can make that grow a lot faster. And there's some really simple things. So we need to scale. Absolutely need to scale. And scale doesn't mean that just Oracle or just an IBM deploys a bunch of stuff for one enterprise customer. That's not enough. We need scale as in everybody in the industry is deploying stuff really quickly, and we need to enable startups to deploy stuff very quickly. It's really important in this space. A lot of the cool applications in IoT will come from startups. They have the cool ideas, and they're not scared to actually try them out. And to do that scale, we really need standards. So that's why I'm talking about standards for a lot of this talk. Standards are important. But we also need to share, because if we want to achieve a lot of this aggregation, if we want to actually make use of data across multiple places, we're going to have to be able to share that data. In sharing that data is going to need trust. So trust and security is something I'm going to be talking about a lot as well. And trust means that we actually have the trust relationships in place between the device and its service, between the service and the user, between the device and its user, between devices. We need those trust relationships in place. And there's no fancy crypto security technology we need to do that. Yeah, we'll have to do a lot of smart things to put those in place, but those are problems that have been solved in the past. But we need to have the mechanisms in place and the mindset of everybody in the industry that they're willing to use those things, right? Not try to reinvent them, but use standard mechanisms. So sharing needs trust. And to do that trust, we really need security. I'm not talking about half-baked pre-shared keys in every device that are easy to crack over time, hard to maintain and upgrade. I'm talking about full-blown PK-based crypto on every single thing, and the infrastructure behind it to make use of it. Provision them, bootstrap them, update them, and then take care of all the authentication and management of that we need to actually make those things participate in services in a secure way from day one. So I think that's another really important thing, is that we can't overemphasize how important security is. And we shouldn't be cutting corners in this space. So that's our vision with little data, getting into big data, and growing. Now let's start talking about some standards. What are the things we've done with this IoT web stack to make this really usable for all kinds of embedded devices? So typically when you look at a web stack and a protocol stack, and I'm an IETF guy, just know my background a little bit. Not a Java guy. I use Java. I've made a company using Java and all across the products. But I'm an IETF protocol guy. This is where I spend my time and my brain power, is working on these protocols. And what we've done at the IETF is we've said that, well, we have a lot of people coming to the IETF and they're working on these things. They're deploying IoT-based systems. They need efficient protocols, efficient security. And over the past 4 or 5 years, the IETF did a lot of work on actually enabling these technologies in much more, let's say, suitable forms for the applications and the devices and the networks. So we have now ways to do, for example, web in 4 bytes of header. It's a new protocol from the IETF called the Constrained Application Protocol, CoAP, which does HTTP for small things and small networks. And so this does rest in a small binary header over UDP. I'll talk a little bit more detail about that. That's one way that we can actually get this web IP technology into a small space. We can do a lot with binary web objects. There's now ways to do binary JSON. There's actually a new standard for binary JSON from the IETF. If you didn't already know about it, it's called CBOR. CBOR. Just ratified by the IETF. Pretty cool stuff. You can actually do complete binary representation of JSON-style structures. And it's a one-to-one mapping. So we can do binary web objects. There's even simpler ways to do that as well. We've done a lot of work around DTLS and the use of UDP. both for getting that asynchronous transaction model that we need in IoT, but also to really minimize the overhead of using full-blown security. So TLS is definitely a core building block of what we're doing in IoT, but we want to make it really efficient. So we don't have that kind of argument when people go and build a system. They say, well, this is so heavy, I don't want to spend the packets to do a TLS handshake. I don't want to spend the bytes to have that record layer to check and encrypt my data. We want to make that as compelling as possible, make that as low overhead as possible, so we don't have those kind of security workarounds. Right? I'll invent something simple because this is hard or big. And we're getting there. DTLS is getting pretty good for IoT, and we have a new version of TLS and DTLS coming out called DTLS 1.3, TLS 1.3, something the IETF is working on right now. And that's for both things like WebRTC, so real-time communications, and for IoT. So it's things like zero round-trip time handshakes we're going to be enabling with TLS. Lower overheads for handshakes. Raw public keys so we can do public key crypto without certificates, just to name a few new features that are coming. So what we end up is the ability over all kinds of IoT kind of backhauls, cellular networks, satellite networks. We can do easily under 100 bytes of overhead for doing real, completely secure REST, object-based communications. And we can do even better than that. So when we get into specialized RF networks, so when I talked about RF mesh, there's a new standard that's actually not so new. It's been out for 5-6 years already, called 6LoWPAN. And 6LoWPAN allows you to do IPv6 over very low power networks. 802.15.4, Bluetooth Smart, low, narrowband telemetry radios, sub-gigahertz radios. All these radios that people used to think, oh, I need this proprietary Z-Wave thing, or I need this proprietary Zigbee thing in order to use those radios. Well, it's not the case anymore. With these new classes of IP protocols from the IETF, the overhead is on the range of 4 to 7 bytes, including UDP. That's nothing. So even when you have a 128 byte frame in some of these radios, we still have plenty of space for the rest of our web stack. So when we get this together and start going over the low power wireless network, we end up with a web stack that's tens of bytes in overhead for the complete packet in order to do really useful things with web. I'm not talking about just a dummy packet. This is a command to turn off your HVAC machine for a period of time with these parameters. We can do that in a packet this size. So this is the new style of web that we're seeing deployed on Internet of Things applications today. IETF I mentioned, this is one important place where a lot of this is happening. If you're looking for specs in this space, it's definitely a good place to look. So there's things like 6LoWPAN. There's a lot of web things going on, like CoAP, REST advice. How do you do REST interfaces for these types of systems? A lot of web linking and things like resource directories. So how do you do search engines for the IoT? Those are being done at the IETF. And that's actually a group called CORE. A lot of work on security. I mentioned DTLS and the new DTLS 1.3 effort that's going on. We'll see a lot more in TLS as well. We're seeing work in Cypher suites. But there's other organizations that are doing a lot of important things too. OMA. OMA is typically known for things like device management. OMA is just finishing a new standard. In fact, I should be in Thailand right now finishing that standard. I decided to come to Java 1 because I thought Java 1 is pretty cool. It is pretty cool. I'm glad I came here. They're actually finishing a complete device management architecture and system for IoT using IETF protocols like CoAP and DTLS. I have one slide on that to explain what that does. Or the IPSO Alliance, the IP Smart Object Alliance, which is working on promoting these technologies and defining the actual web objects, so the semantics. What is location? What is temperature? What is a light control command? Very simple things, but somebody has to define what's in there, right? How is it formatted? So IPSO and OMA together are doing many of those things. Zigbee. even though I mentioned Zigbee as one of these old proprietary things, Zigbee's actually modernized itself. We're now a member of Zigbee. And it's working on things like Zigbee IP and Zigbee IP NAN, which are actually IP stacks. Zigbee has reinvented itself into doing IP stacks and using the Zigbee certification process for making those interoperable. So there's actually IP stacks coming from Zigbee these days. And you can do very low power IP networking, and I mean end-to-end, from the internet all the way down to the Zigbee device using these standards. And finally, there's something you might hear about called 1M2M. You hear about it, don't worry about it too much, because it's something mainly focused on operators. So this is kind of the IMS. I don't know how many of you know what IMS is, but it's kind of the big bad back-end infrastructure that an operator might need to put all these things together. Complex billing systems, complex signaling systems with GSM networks. But we're working with them to make sure that these kind of open standards are supported, because we don't want devices to care, right? Device shouldn't care if it's an operator network or a private service that it's using. It should look exactly the same. So lots of interesting things going on in standardization, and I think my main point here is that these are mostly done. We've been doing these for 5, 6, 7 years already, and we start to have a pretty good toolkit. I'm not missing a lot of stuff, and I'm pretty picky. I want a lot of these technologies. I'm pretty satisfied by this. There's stuff going on, but they're kind of like incremental improvements to things. So I think we start to have the toolkit to go and deploy a lot of systems, and not just like a company like ARM who has resources to, I mean, anybody to go deploy. Small startup, go take a few technology kits and go deploy stuff. That's what we want to see. Oh, this mouse is weird. Random direction. It's okay. This is about the acquisition that happened in the summer. So we used to be an independent company called Sensinode. ARM saw what we were doing in open standards, what we were doing in the use of Java across these platforms for actually deploying software, and was very interested in continuing this. So we are now part of ARM, and what that means is that we have now a much bigger player helping to promote and provide technology around these IoT open standards. And that's exactly what ARM will be doing. So when you think of ARM in this space, don't think of us as a processor technology company. Think of us as a software company doing security and communications tools for you. We're not doing solutions, not vertical markets or things like that, but we're actually providing really nice software tools from the cloud all the way down to devices to help people to deploy these systems. And we, as ARM does, we build an ecosystem around this. So ARM's very good at ecosystems, not just one provider doing something, but building a whole network of companies. The cool thing about ARM is that there's a whole range of processor technologies. So many of you will know ARM from mobile computing, gateways. This is Cortex-A processor kind of class. This is what you're using in your smartphone. If you're an Android developer, this is what you're developing on. But ARM actually focuses a lot these days on Cortex class processors. So Cortex is the class of processors that you see in very small microcontrollers. A Cortex-M0 might be like the tiny, tiny, tiny processor that comes with a temperature sensor, just so you can do that little bus that it uses to talk. Or a toy, for example. Up to a Cortex-M3 or M4, which we can use for a very sophisticated IoT street light with public key crypto and the whole works. Or even a router we can do on a Cortex-M4 with Ethernet and a full IPv6 stack. So a lot of focus on this. And something else you'll see happening is that ARM is doing a lot with servers as well. So there's a new class of A-class processors which are going into real servers. So power efficient, highly cored server clusters. And you can actually see one of those at the ARM booth. So if you come visit at the ARM booth, we have one of these ARM servers up and running. And this is one of the things that makes Java really nice on servers, is that when you deploy this kind of technology for the server side of IoT using Java, it really doesn't matter. Is it an Intel-based server or an ARM 32-bit, ARM 64-bit server? It just doesn't matter. You can still run your same Java code on any of those. I think that's an important thing about Java is it makes us kind of platform independent. The other cool thing about ARM is that we finally start to have a kind of standard in this IoT space for processor architecture. So even though Java does a lot for us, we still in the Cortex-M space do a lot of native development and Java ME development. And in order to do Java ME and get it on lots of places, we actually need to have a platform for it. Java ME doesn't run without something underneath that ties it to the hardware. You need this native piece. And ARM shipped almost 2 billion of these Cortex-M class processors last year, or ARM partners. ARM doesn't actually make chips. It's all the ARM partners that make chips. Out of a total of around 8.7 billion processors in all. And we think that a vast majority of these processors are ready to be connected to services, connected to things. So it is a really big market. And it's a uniform market, right? This is the same architecture of chips. If we can put Java ME onto all of those chips, or at least make it available, that's huge. That's a massive device ecosystem that we can develop Java code on. And I don't know if you follow the latest Java ME8 announcements from Oracle this week. I mean, Java ME8 has become Java again. It's very close. There's some APIs that we don't have, some APIs that are slightly different, but the core of Java is now the same as in Java SE8. And that's a big, big change. So a huge number of devices that we can target with Java ME or with native code when it's appropriate. We have nothing against doing a mix of native and Java when it makes sense.
Was that the price of the sensor, 50 cents?
Those are processors. So you can actually get Cortex-M0 processors today, the whole processor, 50 cents. They're becoming very cheap. You can even get like Cortex-M3s, M4s, which are 32-bit processors. We can do PK crypto on them. We can even run Java ME. They're like $1, each side of the dollar. So these processors are becoming very inexpensive. And so you can build some cool devices with that kind of technology. And you can run Java ME on a lot of those, kind of the upper half of the processors. In this whole processor space, ARM's built an incredible partnership network, and we intend to do the same with IoT. So that's really the way you should think of us in IoT, is that we're providing tools, a lot of support to make sure that there's a huge ecosystem out deploying systems. That's important for us. We want to see this whole IoT space grow. It's good for us in processors. It's good for us in software as well. But I think the important thing is it's good for the whole industry. So that's what we saw happen in mobile. Mobile grew because there was a really strong ecosystem around it. We'll see the same thing happen with IoT. There's no one gorilla that's big enough to grow IoT. There's not even an Apple who can build a walled garden. There's just nobody like that. And I don't think there ever will be because IoT is so many different market segments. So we shouldn't treat it the same way we think of mobile, that, oh, there's an Apple that will control the device and control the service and the music and the... No, we won't have that. You'll have big players. They'll be important. They'll have a lot of technology. Like Oracle is a good example, a lot of enterprise technology, Java technology. But you won't have any one that will control the whole end user application or enterprise application. So partnership's important. We need to actually build an ecosystem around IoT. Okay, let's talk about some details of these protocols. So CoAP I like to call the Web of Things protocol. It's not meant to replace HTTP. So CoAP isn't just a binary compression of HTTP. That would have been a mistake because HTTP actually has a lot of complexity. I don't know how many of you are deep down in HTTP, but modern HTTP, not the one that you see in textbooks, it's complex. We do a lot of stuff with web browsers to actually make HTTP work as it should. And doing a direct conversion of that into a binary UDP world would have brought all that complexity in almost automatically. You'd have to support all those different options and things. What we did instead is we started with a clean slate. We said, well, we want REST. We want something that's completely compatible with HTTP semantically. Get, post, put, delete, URI, media type. That's the important kind of core of REST, it's those things. We want the equivalent of that, but we have some very specific M2M, IoT types of requirements. Some of those requirements are things like multicast. We need to be able to actually do multicast requests. We can do that with CoAP. Very low overhead between small devices and very low complexity. It has to be something that's easy to implement. We needed asynchronous interactions. So in IoT applications, it's not this synchronous polling all the time. We can't do that. We actually have to be able to do a wake up, one-off notification, back to sleep. Without setting up a connection, without doing anything. It's got to be that fast. So that's the reason why we're, for example, using UDP for a lot of the communications. And finally, we need things like discovery and subscription built into the protocol. These are headless devices. We can't, how does discovery work in HTTP? Does anybody know actually what's the discovery mechanism in HTTP? And why there isn't something really built in? It's a really dumb one. It's kind of a trick question. Index.html. That's it. You didn't need discovery in HTTP because everybody went to index.html on a web page. I remember the really old days when we used to do that and type it in by hand. That was your discovery, right? You're a human. You can see the HTML markup. You see the links, and you go there. But we don't have that in these headless sensor devices. So what we did is we built in something similar, a kind of list of links that a device offers you, but we built it into the protocol with a standard format. So now it's kind of a machine-readable list of index.html links. And we get this out of the box with every device that uses this protocol. So very cool protocol, and the other cool thing is it's really easy to proxy into HTTP. We have a full demo of this. I have one slide to show that at the ARM booth in the Congress area. And be happy to just show you how that proxying works, what's happening. I actually have my colleague here, Zin. Zin could raise his hand from ARM. Zin's at the booth, at the ARM booth, so Zin would be happy to show you what stuff we're doing there, practical stuff. There's also a lot happening with 6LoWPAN. This is this RF mesh protocol standard from the IETF. And the way I just like to show this is that there's a lot of variety here. So we talk about IP for IoT. It's not just, we have IPv6 in the Ethernet router and the Wi-Fi router, and thus it works for everything. But there's actually some variations of it for different market segments, because these market segments are pretty different. Building automation, outdoor neighborhood area networks, industrial control, home automation, they have very different requirements. Scale, response times, energy consumption. And so we're seeing a variety of technologies to cover this, but the cool thing is we start to cover it. And so I really want to show by this is that we actually start to have a standard for outdoor applications called Zigbee NAN. We have BT Smart, which we've actually been able to enable with IP technology, something you'll see coming to the market. And we have things like Zigbee IP and something called Zigbee IP 1.x, which is something we're hoping to bring in and improve how applicable this is. And even some industrial control standards. And these are all based on IPv6. So even though we have different variations of these across market segments, we can run IP over all of them, which means we can do things like a web protocol and web security over any of these. So we don't have to change how we communicate with devices, even though it's a different market segment. And that's important for a web developer, right? You're a web developer, you're developing an enterprise application, and you're like, well, I got to get some info from the streetlights in the city because we need to do this. And now I have to get something from the consumer around smart energy and energy consumption. You don't want to have to do that in two different ways, right? You want to be able to do that, manage those devices using the same sets of technologies. Yeah, your payload might be a little bit different. You might use a slightly different payload standard. That's just a media type, right? That's not a big deal. But you don't want to do it in a completely different way for one and the other. So I think this starts to look really good. We start to have IP networking everywhere. A little bit more about the IPSO Alliance. So if something around web semantics for one of these applications is interesting for you, this is an alliance you might want to get involved with. So IPSO Alliance has been around for 5 years. It's an alliance of currently about 55 vendors in the IoT space. Everybody from Google to Cisco to ARM to a lot of smaller companies, energy companies, chip vendors. There's a really good variation of people here, and they know about IoT, so they really know what's happening in this space. And something new that's happening is that IPSO is actually publishing web objects that define how a lot of this automation gets represented. And we're using these at the ARM booth in the demos that we're doing. We're actually using these web semantics. So if you go there and look at how we do temperature or acceleration, it's actually using these standards. So this is something that the IPSO Alliance is going to do more of. Smart cities, building automation, different types of applications in this space. So if that interests you, it's a good organization to get involved with. It's not very expensive to be a member. They just did a new $1,000 SME membership as well, SME and university membership. So it's pretty cheap to get involved. Please.
So when I understand you correctly, the web objects that IPSO defines as basically messages you send around in the IoT network.
It's the media type payload content.
Okay.
Yep. So actually, what IPSO does is they actually take, I'll show it here.
So you say I have a temperature to send around and you'll do it in this format that is defined by
Yep.
the IPSO web object.
So what IPSO actually does is IPSO reuses a standard that's been created by OMA. So OMA has this OMA Lightweight M2M standard that defines that interface between a device and the server, more than just the protocol, the whole interface. How you register, how you configure the security, how you do bootstrapping of your keys and server configuration info, like kind of the whole device management lifecycle. And part of that is that OMA is known, I don't know how many of you know device management for mobile devices, but device management for mobile, you use these objects. They're DM objects. We've created a similar concept in OMA Lightweight, but these objects are very small, very small binary REST objects. So it's like a collection of URIs under a base path, each of which is an integer ID. So you might have, for example, temperature might be object ID 311. There's a registry of those. They're uniquely assigned by OMA. That's the temperature object. So /311 would get you to the temperature object. And inside that object, you define resources. And so /2 might be the temperature value. /3 might be the maximum value. /4 might be the minimum value. And so by doing a very simple URI, /311/4, you've got the temperature. And because it's an object, we can serialize it. So you could just get the temperature itself. And when you do that, we do it a very simple way. Text plain. Media type's text plain. The temperature is 22.3. Don't do any conversion. Just put it in there as 22.3 in ASCII. Keep it simple. But if you serialize the whole object, we have different kinds of serialization. Binary serialization and JSON.
We also have compound objects that combine, I don't know, acceleration, temperature, several things together in one.
You can. So IPSO actually does some of that. So when IPSO's defined these, there's a lot of sharing between these. Because you have an analog maximum value. You have that in almost every one of these. So what they do is they have something called shared resources. So actually are shared resources. These kind of minimums and maximums are used all over the place. And there's a range of resource IDs that's reserved for that. So if you share them across a lot of objects, you define a shared resource. So then if you want to create a new object, you can reuse those. So OMA is actually working on a website for the registration of these where there's tools to actually design your objects. So you could actually reuse, say, there's already temperature. There's already this. I'll just combine them together in a new object. And those can be from a standards body, like IPSO is a separate standards body from OMA, or they can be from an individual. You don't have to be a company, or from a vendor. So there's kind of a vendor-individual space for objects. So this is very cool stuff. And I think it's especially cool because this defines that whole security life cycle. It's not just about the web semantics. It's about actually being able to configure the security of the device. And that includes bootstrapping from a SIM card or a smart card, bootstrapping from Flash, or bootstrapping from a server, a bootstrap server. And it includes both the kind of public-private key certificate-based security and pre-shared key-based security. So you can do both. So this is cool stuff. If you're looking to build a system and want your devices to be manageable, in addition to the protocols, you might want to consider doing something like this on top of that. Right. So how do we put all these standards together? This is important. It seems like there's a lot of these things floating around, but it's actually pretty straightforward. We have devices, and we're seeing those devices speak IP in a lot more places. You'll never get away from these kind of peripheral bus specialized things like Bluetooth. Those still will exist. They have a space. But as soon as you want to build a more complex network, you really can't beat the toolkit we have with IP. We can build real networks with routers, and it's pretty easy to do. So everything from Zigbee IP to Wi-Fi to plain 6LoWPAN networks, we're seeing a lot of IP. We're running security technology like DTLS down to the device. We're not gatewaying the security. So that's a really bad vulnerability here. If you start gatewaying that security, you're in trouble at your gateway. It's a very vulnerable place. So run the security end to end. And then we're running protocols like CoAP these days on these devices that gives us web in a small package. Of course, it's a Wi-Fi device. You might not need something like CoAP. Just run HTTP. If the overhead and everything is fine with you, run HTTP. It's all REST in the end, so it doesn't matter which you use. Back on your backhaul to a service, we tend to use things like CoAP or HTTP with DTLS or TLS. And this is where something like OMA Lightweight comes in to kind of standardize that management of a device. We can do it over cellular. So it turns out cellular has similar requirements for saving bandwidth overhead. So we're applying these protocols over cellular as well. And then if you're an operator doing something more complex, you might consider using something like M2M. Definitely not a requirement. You can do this in a standard Java web infrastructure. You don't need anything special to do it. And then finally, we have web applications. And I think this is very important that we provide interfaces for web applications that are easy, intuitive for a web developer. And that's really HTTP REST. So what we do in our products and in the whole standard space that we work in, we really encourage the use of a simple HTTP REST API, the use of TLS, and the use of appropriate security models. So a lot of the time, especially in our products, we're managing the security domain here. This is a complex thing to manage, all the provisioning and bootstrapping of keys. And here we would deal with accounts. We deal with web application accounts. What domain do you have access to at what level? So something that the users here or the developers here understand. We really match those two security domains. This is typically on the same server or the same cluster, so you're not usually very far away. This is how we put these things together in the end. And what you get is end-to-end REST. That's what you see in the end from the developer point of view. So it's kind of a transparent REST down to IoT devices. This is the demo setup that you'll see us showing at the ARM booth, as well as the Oracle booth. So we have pieces of this in both places. We're showing some pretty cool things. So starting from the embedded side, we have the world's first set of these protocols working on Java ME. We're showing that for the first time at Java 1. So you see a Java ME. This is still Java ME 3.3. ME 8 was really just released. We didn't have access to that until now. But our next version will be supporting ME 8 fairly soon. And that's working on both Kyle and Freescale K70 boards. We have some embedded C-based devices as well, using a native library. This is a very small Cortex-based chip. And the cool thing you'll see there is it's the same protocol, the same web objects, the same interface. So it didn't matter was it a Java ME-based device or a C-based device. What matters is the developer got a hold of the technology that worked best for them. We have a Java SE embedded-based gateway. This is a Freescale IMX-based processor running Linux. And we're doing some distributed directory technology. So we have directories we use for keeping track of all the devices. We actually distribute some of that from the cloud into the gateway. And we run that on Java SE embedded. So these guys actually register here. They don't know about the cloud. They don't care about the cloud. If the internet connection stops working, these still function. And Oracle has some work they've done on complex event processing. So doing some event processing, producing new resources out of things that happen here. We're speaking CoAP and Lightweight M2M all the way through, back to a cloud platform. This is one of our products. It's the connector for the cloud. We don't do application servers or full vertical applications. We just do the communications and security connector. And that's a Java SE component. We are working on Java EE as well, so to run this as a container. And we do things like load balancing. We scale out across big clusters. So this is kind of a millions to tens of millions of node type of scale server component. Nodes, I mean these guys. So we think in terms of streetlights or electric meters. How many of those can we talk to with one server cluster? And finally, we're showing some web applications that's something we just provide as source code. It's just normal Java JSP that we use to do a web GUI, and something we provide as a reference application to developers. And just to show how normal this development is, it's nothing special. It's no different than any normal JSP-based project. Only difference is now you just use this REST interface to access IoT data rather than something more specialized. And we have some future roadmap stuff we're working on. So we're working on things like identity management, integration with Oracle tools. We're working on big data integration with the whole suite of NoSQL, Hadoop-based technologies. We have Java FX-based UIs. If you go to the Oracle booth, there's a demo with this one box talking to local sensors, a local Java FX-based UI. That's a very cool part of this demo too. So you can see that at the Oracle booth. So lots of things going on in this space. Integration of IoT with the Java and Oracle ecosystem. And finally, I recommend people to go check out the Embed project as well. This is something we're doing to kind of provide we like to call it kind of the Android for IoT. We're really providing a very simple SDK that you can use across all Cortex-based devices at about 2 billion and growing. That's a pretty big device space to get access to. And we're including things like these protocol stacks, 6LoWPAN, CoAP. We're actually providing those libraries in the near future on Embed. And I think we'll see more things around Java ME support, things like that with Embed in the future too. So there's a Java connection here as well. So we want to see Java running on a lot of these devices, running Embed. So embed.org, easy development for embedded devices. Finally, a summary, lots of stuff, I know, don't worry. You can look up all this stuff, you'll find these slides. If there's something that interests you, you can definitely get more information. You can always feel free to ping me. I'm always happy to answer people. Or, for example, my colleague Zin at the ARM booth. And we'd happy to talk about all this some more. Some things I like people to go away with, pretty simple. IoT is just an evolution of the web. So if people talk to you about IoT, this, that, it's a big thing, level head. It's just web and internet technology. We're just applying it to a new domain. That's it. So we know how to do this. We've done this before. Market growth, so our scale, it'll be driven by standards and time to market. So the combination of these things, if somebody tells you that standards are not important, they don't really know what they're talking about, because this is such a complex ecosystem. We need those standards to be able to scale these systems. But we need to make the tools that get this stuff fast to market. Right? It's not enough to have standards. If the standards are very complex to use and deploy, it didn't help us anything, right? I mean, it just made it worse. So we need standards and tools. And finally, in addition to the standards, trusted security. We always have to emphasize that. So both for the consumers and for the end users, like enterprises, and just so that we're building technology that really is manageable. So going out and hand updating devices because you just compromised, 300,000 electric meters, that's not fun. Companies have folded because of this. In Sweden, for example, there was a case of this, and there was a whole company that folded because they just got caught in a maintenance nightmare with these IoT devices. They had to go out and roll trucks to update devices that had security issues and some other reliability issues. So you have to be really careful with the kind of maintainability and security. And finally, big data needs little data. And that's what we're here to do. We're little data guys. So we want to feed all this data and make it available for big data enterprise developers. I think that's where we'll get the cool stuff, building neat applications over this. That's it. Thank you. So happy to answer any questions. We had a couple during the talk, but.
I would like to hear what you think about your CoAP proposal compared to MQTT. Because I think this is a protocol that is also discussed a lot as being the new standard of communication in the Internet of Things.
It's a good question. So, yeah. I don't particularly like MQTT all that much, personally. But we're all techie nerds, right? So we all have our personal opinions. I don't typically like it because MQTT is one of these protocols that it's been around for a long time. It's not new. It's legacy. It's as legacy as you can get. I mean, we're talking late 90s. And it was one of these things that they said that, well, we want to do pub sub. So how do we do pub sub? We reinvent everything. The architecture, the infrastructure, the protocols, you really reinvent it all. And I don't think that's a very productive way to design protocols and get them out there. So I think there is a place for pub sub, but do we need to reinvent the entire stack to do that and have special tools, special brokers, special protocols? No. People do pub sub on HTTP today, on REST, and it works just fine. People can do pub sub on CoAP right now. You can do pub sub. It's just a REST protocol, and it will work just fine. So do we need to invent a new protocol to do pub sub? Probably not. You have things like XMPP as well that work fine. The secondary thing about MQTT to understand is that MQTT is actually not solving the problem that CoAP's solving. I don't actually see CoAP and MQTT competing at all. MQTT is competing against the use of HTTP for solving a lot of these systems, and as a different paradigm, a pub sub paradigm. So if you want to do pub sub in particular, and you want to use that as an alternative to HTTP, I hate that. We lost our battery. It still works though, huh? Wow. How is that even possible? Oh, it's wired. Okay. Good. So if you want to do pub sub in particular, and you want an alternative to HTTP, that's where MQTT would be useful. But for really small devices like we've been talking about here, small networks, MQTT is still too heavy for really use in that space. So what I hope to see in the future is that some of this pub stuff really gets brought back into the web world, so we can do pub sub over standard protocols. It would be so much easier, right? You reuse your Jetty infrastructure, or your web application server infrastructure for serving all this stuff up, load balancing, and then you use REST semantics for pub sub, and then you're fine.
Zach, you mentioned about XMPP for publish subscribe. It offers some encryption capability built in. So how's XMPP compared to CoAP?
So XMPP does some really cool pub sub stuff, and there is security built in, but it's pretty heavy. I mean, it's a little bit like MQTT in that way, that it wasn't really thought of for really small devices. It was developed at a time where you're working with bigger devices. So they're pretty simple. I mean, XMPP uses an XML stream to do those things. MQTT has its own framing. That's about the difference. Both of them have some ways you can do security, et cetera. So XMPP is popular for Jabber type of chat applications, but it's found a lot of new applications out there.
So within the protocols that you already presented now, for me as a Java developer in this area, how much tool support and libraries do I already have available?
So CoAP's a fairly new protocol, but we have a pretty rich open source and commercial library selection. So there are a bunch of open source projects available for CoAP on Java. There are commercial tools available on Java. So for example, ARM provides commercial Java libraries for SE for use in the cloud, SE on gateways, and now ME. So it's pretty complete. And there's projects like Californium. That's a pretty good one for Java SE that's open source. And we'll be much more active in open source in the future as well. So I think for CoAP especially, we'll get a lot of support. DTLS needs some more support too. So we've been encouraging Oracle and all of our partners to do more on DTLS, because the DTLS support in Java today is a little bit iffy.
Sam, one more question. CoAP using UDP, is the advantage is the speed. The disadvantage is it when the receiver cannot receive the transmission, it doesn't retransmit. So it's putting the burden on the receiver to make a second request?
Not exactly. So CoAP actually builds in a reliability mechanism into the protocol. So it's true, the protocol has to implement its own reliability mechanism, but it's a simple binary exponential backoff. So TCP is trying to do something a little bit different. So the way TCP does reliability, it's trying to maximize performance really as a stream. So the binary backoff in CoAP is a lot simpler. It's just per datagram and one datagram at a time. So there's no flows. There's really just one packet at a time. It's n start equals 1 in CoAP. So it's not trying to maximize performance. It's trying to minimize overhead. It's a different goal.
Does OAuth fit into any of the devices talking to each other way down to low level? Is there any way?
OAuth probably doesn't go down that deep. We start getting into OAuth like at the edge of our cloud connector, and that's when we start to need to hook into user accounts. But it's a good question, because we are going to see the need for more and more authentication technology down to devices. It won't look exactly like OAuth, but it may have some of the same kind of features. So we do need to do things like get an authorization token to talk to another device. So if we two devices want to talk to each other, we have to talk to our mothership and figure that out. There is a lot of talk right now in the IETF about that kind of thing. So I think we'll see more of it. I think there was a question I missed in the back, sorry. No? Okay. Great. Thanks everyone, lively audience for this time in the morning. So welcome to the ARM booth and the Oracle booth. Just come by and say hi, and otherwise enjoy your day at Java 1.